So the title has originally been the expiratory time constants in mechanically ventilated patients, but since Zoli put in addition to that, it's exhalation unbiased, I kind of liked it and left it there since. So what is a time constant? Time constant is time to exhale 63% of VT, tidal volume. That's what it is, nothing less, nothing more. Because we know, if we take a look at the flow volume curve, it resembles exponential decay. It's not a straight line, it's rather exponential. Time constant is, however, much more frequently obtained from multiplication of resistance and compliance that require expiratory and inspiratory holds. So the first measured, it's quite easy to measure. The second, it's a little more complicated and needs some interference with the ventilation. Reference values used to be between 0.5 and 8 seconds. This is what you can find in most studies. So quick equation, time constant as a product of resistance and compliance. If we cross out the centimeters of water, we'll end up with liters per second. If we cross out the liters, we'll get seconds. So where's the devil hidden? When we teach passive exhalation, we try to replace the complexity of respiratory system by a single balloon and a fixed resistance, like you see in the balloon and the tube. But reality is much more complex. When we try to measure the time constant by its definition, and definition says that each of the differently exhaled volume, so 63, then additional 23%, additional 9, this is by definition, those time intervals should be equal. Well, that's where the term constant comes from. But the reality is different. When we did the measurements in post-op patients with protective tidal volume, we found totally different thing. The first time constant, second and third are progressively shorter, and that is where the constant just vanished from definition. So the third time constant is roughly half of the first. So the time constant itself, as per the definition, does not exist. So why is that? When we look closer at the physiology and the most notable studies, we'll find what influences the time constant. First is the tracheal tube. We know that the tracheal tube is major resistance because of its most thin diameter in the ventilation circuit. And the study by Gutman showed it 30 years ago. He found out that the time constant, or lung emptying of the first 60% of the total of the respiratory system alone is significantly shorter, probably 3 times less. When we intubate the patient, it becomes 3 times longer. We're still talking about the first time constant, the time constant measured as the first 60% of exhaled volume. So the endotracheal tube is the sole cause, or the most important cause, why we see this inequality. Second is the tidal volume. And this is closely related to recruitability. So if tidal volume increases, the lung emptying prolongs. So the time constant is longer. So we've performed, in the COVID era, we've performed a trial where we measured 54, or we performed 54 PEEP titrations in COVID alpha patients in both prone and supine positions, and we divided them. This was ventilation, pressure control ventilation with a fixed driving pressure of 14 centimeters of water, and we have observed 2 patterns. So as the PEEP increases, the recruitability goes up, the time constant goes up. For those who do not have recruitable lungs, as you can see in the B figure, it goes down mostly. Third and the last is lung heterogeneity. We know that we cannot replace the complexity of the respiratory system with a single balloon to demonstrate lung emptying. So if we performed electric impedance, we do see regional time constant heterogeneity. The figure B is the airdiazed pneumonia, and you see how relatively tight the time constants are across the respiratory system. In the COPD patient C, with the expiratory flow limitation, the time constant heterogeneity is larger and moved to the high regions. So these four things or determinants are the reasons why the definition doesn't hold. So we can observe the flow volume curves on the ventilator, and that's quite easy to do. The more problematic is that we are missing the objectivity here. So time constant gives us only one number, and that number is mostly related to the first half of exhalation. But it's still better than nothing, because I am personally not aware of any numerical expression of the flow volume curve other than the expiratory time constant, because it considers flow and volume at the same time. How can we obtain it? So, as a means of lung emptying, there are different ventilators providing different means of determining time constants. Most common method is multiplication, so resistance, time, compliance. For that, you need hold maneuvers. So you have to arrest the ventilation at the end inspiration and end expiration. For example, Macket servo U, servo I ventilators do that, and they will not provide values for time constant unless you do the hold maneuvers. Hamilton ventilators derives the time constants from the early exhalation, so from peak expiratory flow to 75% of the volume. So they do show the time constants, but they use it mostly for intelligent optimization. Measured time constants is rarely displayed on ventilators, only on some. We've performed the trial in 30 post-op patients where we try to determine the time constants using different methods in both pressure and volume control ventilation, and we found that it doesn't matter which mode you use. So what is perhaps or seems to be most valid is the measured time constant, because it has the more little spread. This is the first blue bar box plot. Oh. Now, why it is exhalation unbiased? When we have inspiration mechanics, we all relate or we all focus on inspiratory mechanics. So we control the ventilation, we control inspiratory pressure, we control the volume, we control the duration and the rate. So what we set up on the ventilator, the compliance and the resistance is resulting. But if you consider measured time constant, it's something that should be less biased because it comes out. When the ventilator turns off the inspiratory phase and switches to exhalation, you just record the volume to passively exhale the 60% of ET. So based or compared to compliance, this should be less biased. Okay, so when to use it, or why to use it? First, as we mentioned, because there is no number to represent the flow volume curve. Second, assessing changing lung mechanics. Similarly to compliance and resistance, if the lung mechanics changes, if the pneumonia improves, if the pulmonary edema resolves, the lung emptying becomes different. Inspiration as well. So we can see it instantly if we had the measured time constants readily available. So we see the change in pathology. Third, auto-peep. We know that if curve doesn't return to zero, there is high chance that there is auto-peep going on. But seeing the time constant value gives us at least some clue about the respiratory rate. If the time constant is short, we can move to higher frequencies. If it's long, we should slow down or change I ratio. Meaning, if we see extremely short time constant, it means the the pathology didn't improve significantly, and we should probably not wean. These data, we do not have much studies to prove, but it's logical if we have really short time constant that the mechanics is not good, because it's passive and it's fast. And then fifth, most ventilators use either time constant, which is the proprietary version of Hamilton interval event, or very closely derived variables. They do not call it time constant, but they use it to regulate the end of inspiration or targeted respiratory rate. So, how I use time constant? I used to use the time constant for an unknown patient in the middle of the night. It means that when I connect somebody to the ventilator, I have no idea what the exhalation is or what the lungs are. We have no idea whether COPD with concomitant pneumonia produces different time constant. COPD should be giving us long time constant. Pneumonia, on the other hand, if it's not recruitable, it should be short. But as you'll see in later slides, there is a so-called pseudo-normal tau or pseudo-normal time constant that is a crude average of both pathologies. And second, I sometimes use it to titrate PEEP. We've published a study in the BMC anesthesiology a few years ago. Again, a PEEP titration from the previous trial where we compared compliance with the time constant. And as you can see here, in both recruitable groups, those patients lying on the back and those being in a prone position, the average values were relatively close. Although in supine position, the tau time constant seems to be more sensitive to overdistension. This relates to the electric impedance study that we've performed, but we didn't publish eventually because the number was too low. So the overall mechanics was similar, although it different from the patient to patient. An interesting study was published 12 years ago from a US researcher, Ravas, and he did, for me, quite interesting thing. He calculated the time constant, and he used these equations to calculate plateau pressure, compliance, and total resistance without interruption of breathing. So basically substituted time constant, placed it into the equation, and got exactly the same values as he would if he arrested ventilation. So if he performed the inspiratory and expiratory poses. So my question is, why is it still not in the ventilators? Why is it still not seen on the front screen so we can see how does the lung behave passively when the ventilator turns off? We've published quite extensively on this topic, but we've concluded with the narrator review on the time constants. And in that review at the end, we've published a figure, like so-called diagnostic algorithm, how we should look at the time constant and how it can help us. This is quite basic physiology. So if the time constant is within normal range, 0.5, 0.8 can be either normal or pseudo-normal. It means the mix of obstructive and restrictive pathologies, so the overall time constant is within the normal range. If it's short, we likely have fast pushback from the lungs. So usual pathologies are non-recruitable areas, fibrosis, pulmonary edema. These are common pathologies that we can see. And if the time constant is too long, we can have either physiologic issues such as very high tidal volume, which is not protective, or diseases like COPD, emphysema, asthma, and this is associated with early airway collapse or high resistance. And then we should optimize. It's another piece of the puzzle, not a solo parameter to guide therapy. So due to its limitations, it's simple, non-invasive bedside and could be viewed on the breath-to-breath basis if the ventilator companies decided to put its measured values in. It's a measure of improving worsening, just like the other mechanics, although, again, if you want to have reliable static compliance, you have to have hold maneuvers. With the measured time constant, you don't. And therefore, should be less biased. So the question is whether we should make it a routine assessment. Thank you for your attention.